The James Webb Space Telescope and Hubble before it have spent decades between them producing absolutely stunning observations of our universe in unprecedented detail. But a quick scroll through the Wikipedia list of astronomical observatories and you'll see dozens of telescopes around the world or in space, with loads more proposed or planned. But if JWST is so good, then why do we want to build more? There has to be some reason for astronomers to want more and more and more telescopes, and it isn't just because we want more shiny new toys. What if I told you that the James Webb Space Telescope just isn't enough, and that it can never be enough for the field of professional astronomy? Before we go any further, make sure to subscribe and hit the bell icon so you don't miss future videos. Now I know you've seen loads of images from JWST and Hubble, and it's entirely natural to be saying, but Thomas, the images are amazing, why on Earth, or in space, do you need more telescopes? To answer that question, we need to talk about light, and specifically how light travels from distant objects out in space to reach us here on Earth. Ultimately, it comes down to two major physical factors: emission and absorption. Let's start with emission. Put simply, emission is the family of processes that let objects give out energy as light. This can take many different forms. Atoms in ionized gas clouds emit light when they capture electrons. Energy is released in that process as photons of light with specific energies set by quantum physics. Stars release energy through nuclear fusion reactions, turning primarily hydrogen gas into pure energy, emitting that as light. The hotter the star, the brighter and bluer that light is. Everything that's got any temperature, so everything in the universe, will emit light to release heat. We do this ourselves. It's why we show up on infrared thermal cameras. But in space, it can release immense amounts of energy, like from the gas and dust orbiting supermassive black holes at the centre of galaxies. And then there's the weird stuff, like light emitted by electrons as they spin around magnetic field lines in the outskirts of galaxies. All of this emission, these sources of light, they send light throughout our universe, but you'll notice that our sky is still pretty dark to our eyes. This is because not all of this light is visible. It spans the entire electromagnetic spectrum. The ionized gas clouds releasing energy as they capture electrons, well, most of that light tends to be quite low energy, with wavelengths longer than we can see. Loads of it's in the infrared or the microwave parts of the EM spectrum. Starlight? Okay, yeah, that tends to be visible, or at least some of it is. Stars emit light over a wide range of wavelengths, with the strongest frequencies or wavelengths of a given star determined by its temperature. For the most massive stars, the big bright blue ones, their peak wavelength is actually shorter than we can see. It's in the ultraviolet. Those accreting supermassive black holes with their bright spinning disks around them, the temperatures there can get so hot the light given off can be seen in X-ray light, very, very short wavelengths. And at the complete other end of the scale, well, there's the light given off by electrons spinning around magnetic fields. A lot of that is seen in the radio. So we have light across the EM spectrum. Job done, problem solved, we just need telescopes across the EM spectrum. Not so fast. If that was the case, we would just build one telescope for each bit of the EM spectrum and be done with it. But we built the James Webb Space Telescope. We must have done that for a reason. And one of those reasons is gonna sound really dull. It's dust. Now I know what you're thinking. It's not this sort of dust, the sort that accumulates annoyingly quickly in your house. This is cosmic dust. But actually it has a pretty similar effect. Dust is one of the main causes of absorption. Now absorption is just a fancy way of saying that light gets blocked and absorbed by something else. It can be a really useful tool. We use it to figure out what things are made of, because different atoms and molecules absorb different wavelengths or frequencies of light. It's how we discovered that the sun was made of hydrogen and helium, and that there is water in the atmospheres of some exoplanets. Every atom and molecule has a bit of a fingerprint. But absorption can also cause a massive headache for observers, particularly when that absorption is from dust. The Hubble Space Telescope is amazing. It's given us astounding images of the universe, and it's been responsible for countless scientific publications. Okay, someone's probably counted, but I haven't. But it has a huge issue. Visible light, the light that we can see and that Hubble was built to detect, is really easily blocked by dust. That means in all of these images of nebulae, we can't actually see the forming stars or really any of the structure in there. There's just loads of dust in the way absorbing that light. Fast forward a few years to the launch of the James Webb Space Telescope, and now we can see through that dust because the infrared light that JWST detects has wavelengths that are a bit longer than the dust in these regions. That light can get through. With JWST, we see so much more detail in the Southern Ring Nebula. The light from the stars is detected so much more easily, and we see the structure in the gas and dust of the nebula that was completely missing in the Hubble image. And while this is incredible, I told you JWST isn't enough, and that's true. It can't give us the full picture. Let's look at something a little bit bigger to show you why. This is a galaxy called Stephan's Quintet. In reality, only 4 of these galaxies are actually interacting meaningfully through gravity. This spiral galaxy down here, it's photobombing the scene some 40 million light years away from Earth. The rest of the group, it's like 300 million light years away. This image is one of the first we got from the James Webb Space Telescope, so we're viewing this one in the infrared. We can see nice structures in these galaxies, as well as the faint glow of gas in this tidally disrupted tail, gas that's been pulled off the galaxy by the gravity of another. Let's shorten our wavelengths a bit into visible light, with this now being a Hubble Space Telescope image. We see a lot more of the bright emission from this photobombing spiral galaxy, from all of the young stars and regions of ionized gas that we see in that one. In the other galaxies, these redder galaxies where there's very little star formation happening, we see more light being blocked by dust, particularly here and here in the centre. But as I said, these galaxies are interacting. Well, 4 of them are. We saw this tidal tail in the JWST image. It's not as clear in visible light, but what if I told you that this galaxy here, the S-shaped one in the centre, is actually colliding with the rest of the group? Can't see it? Yeah, me neither. Let's add data from one more telescope, the Chandra X-ray telescope. Oh yeah, there it is. What we're seeing here in the X-ray, that we couldn't see in visible or infrared light, is gas interacting. You see, there's more to galaxies than you can typically see. Around that familiar disk of gas and dust, there's this extended envelope of gas called the circumgalactic medium. This is actually what I study in my own research. What's happening here as this galaxy crashes into the rest of the galaxy group is the gas in the circumgalactic medium of the incoming galaxy is smashing into all of the gas around and between the other galaxies in the group. Because the gas is colliding so fast, there's a sharp pressure change occurring at this interaction called a shock. That shock heats up the gas so much that it emits X-ray lights in this band at the leading edge of the incoming galaxy. Without observations in the X-ray part of the spectrum, we wouldn't see what's going on here. We wouldn't be able to get the full picture. But by far, the best example for the need for multi-wavelength observations is the plane of our own Milky Way galaxy. This is how our view of the universe looks in visible light. This is an all-sky image from the Gaia satellite. And across the centre of this image, we see the plane of the Milky Way. But let's leave that behind for a bit. We're going to look to some longer wavelengths first in this all-sky image from radio light. In the centre, we see a strong region of emission from the centre of the galaxy. This is where we find the supermassive black hole, Sagittarius A star. Now, Sagittarius A star is surrounded by a load of material that gives off radio light. This is the same light that was used by the Event Horizon Telescope collaboration to produce this amazing image of the black hole itself a few years ago, or at least its shadow. Away from the centres, we see some bright spots of light from supernova remnants and other regions with black holes, and down here we see a couple of faint smudges. But let's have a look to some shorter wavelengths, maybe we can see what those are. Now in the infrared we can see what those objects are a little bit better. These are the Large and Small Magellanic Clouds, satellite galaxies of the Milky Way, a few 100,000 light years away from us on Earth. We can see some of the structure in the LMC in this image, but it doesn't really look like a galaxy yet. Looking back to the Milky Way, we can see more emission further from the centre than we did in the radio image. This shows us where gas and dust are located and where stars are forming in these small bright spots over here. Coming back to Gaia's visible light image, we can see the Magellanic Clouds looking a bit more like galaxies now. But the real star of the show is the plane of the Milky Way. We see starlight from the disk, but in front there's these huge cosmic dust clouds blocking so much light from the centre of our galaxy. And it's really limiting our ability to study stuff going on in there. Going shorter still into the X-ray, dust is, if anything, just a bigger problem. But we can make out some emission from the massive blue stars of the disk, and we see this spectacularly bright emission from the Cygnus superbubble, home to the first confirmed black hole, and from the Vela supernova remnant over on the right. We can also see emission from this outflowing gas shooting up and down from the galactic centre into the Milky Way's circumgalactic medium. And looking to the most energetic light, gamma rays, in this image from the Fermi Space Telescope, we actually don't see the effects of dust anymore, really. Here we see a number of sources across the sky, but the real star of the show is this strong excess in the centre of our galaxy. We don't actually know what this thing is, we see it in the Andromeda Galaxy too. The most likely answer is some currently unresolved millisecond pulsars, neutron stars, that spin thousands of times per second. But there could be other answers. One idea includes that it could be a signal of dark matter and anti-dark matter colliding, being destroyed, a process called annihilation, and then releasing all of that light as gamma rays. Now I know that was a bit of a whirlwind of information to land on you all at once, so let's have a look at what changed as we went through the spectrum. We saw that the supernova remnant was visible in the radio, but then not in the infrared, and infrared's where JWST observes. But then we looked at it in X-ray and it was visible again, so JWST would have missed that. Visible light, ultraviolet and X-ray light showed us the light from young, newly formed stars, but only in the infrared could we see the light from those stars that are still forming. So I hope that you agree that having telescopes across the EM spectrum is important, not just to detect the emission from different objects, but also to let us get at the light, no matter what's in the way. We need all of these new telescopes like the Vera Rubin Observatory, the Nancy Grace Roman Space Telescope, the Habitable Worlds Observatory and the Square Kilometre Array. Not because any of them will be the final answer to astronomical observations, but because alone, just like JWST, they won't be enough, and they can never be enough. Thank you for watching this video all the way to the end, and particular thanks go to my patrons over on Patreon who make these videos possible. The names of my Education Enabler patrons are on screen now. All patrons get early access to videos and an exclusive monthly behind the scenes vlog. For more information and to sign up, go to patreon.com/Thomas Rintoul. This topic, multi-wavelength observations, is something I've been wanting to cover for a while, because it's so easy for people to get caught up in the hype around NASA's latest big telescope, and then to just assume that's where all of the best discoveries are coming from. It's also something I have to consider in my own work. I'm a simulator, but what I work on, the circumgalactic medium, is observationally a multi-wavelength problem. We have hot gas, which we call cool gas, and we have incredibly hot gas, which we call hot gas, in the CGM. And those aren't generally observed by the same telescopes. They emit different wavelengths. So I hope you found this interesting. I mentioned a few new or upcoming telescopes at the end there. If you want to know more about them, let me know in the comment section down below. And if you have any ideas for future videos, also let me know down there. If you're looking for something else to watch, here are some videos I prepared earlier. Thank you again for watching. Make sure to do the YouTube pleasantries on your way out, and I will see you in the next one.